Section 9.10, Taylor and Maclaurin series. We have seen that sometimes a function can be represented by a series, like we did one for inverse tangent x. We showed what ln of 1 plus x converges to. So we have lots of different series that converge to specific functions. Now we want to look at the general case of a power series that could represent a function in general. So functions cannot always be represented by power series, but sometimes they can. And if they can be represented by a power series, then this is what that power series is. We would say that the f of x is equal to the sum of n equals 0 to infinity of c sub n x minus a to the n, subject to the condition that the x is within the radius of convergence of the series. And that radius of convergence might be 0, so there might be not a whole lot of convergence available. But we're going to see some series that have infinite radius of convergence and are therefore extremely useful. So if I do have a power series representing a function, so I expanded out the terms here. What does this mean, the sum from n equals 0 to infinity of c sub n x minus a to the n? It means we got c sub 0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed, etc., and so on forever. So it actually turns out to be feasible to get a handle on what all these c's are if you know something about the derivatives of the functions. So now that we understand that you can do derivatives of these series, all we have to do is look at what f prime of x is. So f prime of x is the c0 will go to 0, so I'll have a 0 term, and then x minus a, we can think of that as a u substitution, u equals x minus a. Well, actually, it's a chain rule in this case. So we do derivative, c1 times x minus a is just going to give me c1 x minus a to the 0, so that goes away. I do have a chain rule, but the chain rule is just, the derivative of the inside function is just 1, and that continues to be the case throughout. So then my next term is going to be 2c2, just using power rule, 2c2 x minus a, and we're dropping that exponent 1, so x minus a to the 1. There is, again, a chain rule, times the derivative of the inside function, but the derivative of the inside function is 1, so I don't even have to write it, and then we'd get plus 3c3 x minus a squared plus, and so on. All right, so here's the trick that we can pull to get a handle on what these things are, which is, what about when x equals a? So when x equals a, all of these terms are 0. So all I would have is left from this original function, f of a equals c0. So I already know that the c0 is just f of a. All right, now looking at this derivative, we can also look at when x equals a, what am I going to get? Well, my f prime of x is going to be f prime of a. It's going to equal c1. And then all these terms are going to be 0 because x equals a. So now I know that c1 is f prime of a. Now I can keep doing that. So I'll do f double prime of x. So the c1 is going to become 0 again. Now I'm going to have just 2c2 for this term. This term I have to do power rule, so I'm going to have plus 6c3 x minus a. And of course, the next term after this would have been 4c4 x minus a cubed. So that means that my next term here is going to be 12c4 x minus a squared. And so on. Here's just put in the next one because we're going to have to keep doing this. The next one is going to be 20. You can work out to see why that is. 20c5 x minus a cubed. Yeah, so that's what I got so far. So what I can, and then we keep doing this. We just keep saying what happens when x equals a. Then I'm going to have f double prime of a, and it equals 2c2. So what that tells me is that c2 is equal to f double prime of a over 2. So I just keep doing that. I'll write out one more and then we'll get the pattern. So the third derivative, keep doing the derivatives of this thing. The third derivative, now this is a constant, it's going to go to 0. This term is going to become 6c3. This term I'm going to do 12 times 2, so I'm going to get 24c4 x minus a. This one is going to become 60 c5 x minus a squared, and of course these sums all go on forever. So then when x equals a, f triple prime of a is equal to 6 c3, right? Because this 6c3 is going to be the only non-zero term. So that tells me that c3 is equal to f triple prime of a over 6. All right, so when I keep doing this, I'm going to find out that when I do the fourth derivative of x, it's going to be, this is going to give me this one, 24c4. The fifth derivative is going to give me 120c5, and so on. So really the fifth derivative evaluated at a, following the same pattern, evaluate when x equals a. It's going to tell me what each of those is. So in general, what I'm going to have is that the Cn, well, let's solve these ones. So C4 equals F4, the fourth derivative of a, at a, over 24. And then I have C5 is going to be the, I'm making mistakes all over the place. That's a 5 right there. C5 is going to be the fifth derivative. That's how we write the fifth derivative of f at a over 120. So if we get a handle on what these denominators are, they're n factorial. So in general, Cn is equal to the nth derivative of f evaluated at a over n factorial. So if the series converges, if f is represented by a power series, then we know what that series has to be. The f of x equals the sum from n equals 0 to infinity of the nth derivative of f evaluated at a over n factorial. And remembering that these were just the coefficients, there's a term x minus a to the nth power. So if I sort of write those out a little bit, there's an interesting observation we can make, because f of x equals, so when I use n equals 0, and by the way, we're always saying 0 factorial is equal to 1. So that's a definition of 0 factorial. So when I put in n equals 0, I'm just going to have the 0th derivative of f of a. What does that mean? That just means f of a. So it's going to be f of a over 1, f of a over 1, times x minus a to the 0 power, which is just 1. So I just have f of a. And then when n equals 1, I'm going to have the first derivative of a over 1 factorial, so that's just f prime of a. But now I'm going to have x minus a to the 1, so I have to write that, x minus a. And then my next term, when n equals 2, I'm going to have the second derivative evaluated at a over 2 factorial. It's really just 2. I could write 2 factorial if I want, times x minus a squared. And then this keeps going, so I have f triple prime of a over 3 factorial, x minus a cubed, etc. So what's cool about this is, remember linear approximation? That's your linear approximation formula. It's just 2 terms of this power series, which is called a Taylor series. So this is called a Taylor series, and it's an expansion of linear approximation. So what we're going to look at next is, when does this converge? How many terms do we need? Things like that. And we'll try actually representing some functions by this, because it turns out to be fairly doable.